Welcome to the Deep Dive. Today we're looking at something pretty interesting, right at the crossroads of AI and, well, practical problem solving. How do you take these tricky real-world business challenges and turn them into math models that a computer can actually optimize?
Yeah, that's the classic operations research challenge, isn't it? It usually takes specific experts.
Exactly. People who know the business and the math. But what if AI could handle that?
Yeah.
We're diving into some research proposing exactly that in AI agent for the whole process.
That's right. I mean, operations research, or OR, it's super powerful for optimizing logistics, scheduling, you name it. But historically, it's been a bit gated.
Gated!
Yeah, you needed those OR experts, the modelers, the programmers. It's costly, time-consuming. This paper introduces something called OR-LLM-Agent. It's pitched as the first AI agent trying to automate that entire pipeline end to end.
Okay, so potentially huge for businesses without those dedicated OR teams.
Absolutely. Imagine democratizing that optimization power.
So this OR-LLM agent, it leans heavily on large language models, LLMs, like the tech behind ChatGPT, right? But specifically, their reasoning ability.
Precisely. It uses a technique called chain of thought, or COT.
Chain of thought. How does that actually help turn, plain English into a formal math model?
Well, think about how you solve a complex word problem. You don't just guess the answer.
Right, you break it down.
Exactly. You identify variables, constraints, the goal, step by step. COT prompting encourages the LLM to do the same thing, show its work, essentially.
So it articulates its reasoning process.
Yeah, instead of just spitting out equations, it outlines the logic, the structure. This usually leads to a much more accurate mathematical model, often in LaTeX format. It's more nuanced than just keyword matching.
Okay, makes sense. And it doesn't stop at the model, the blueprint. There's this other piece, OR code agent.
That's the next step. Once you have the mathematical model, the OR code agent takes that blueprint and generates the actual code.
Code to run on specific OR solvers, like Gurobi, know how to operate the specialized software.
Exactly. It translates the math into, say, Python code that Gurobi can understand and solve.
But writing code for complex math models? That sounds error-prone.
It definitely can be, and that's why the OR code agent has these built-in checks. It runs the code in a sandbox.
The safe testing area.
Right. If the code crashes, throws an error, whatever, the agent doesn't just fail. It has a self-repair mechanism.
Self-repair? How does that work?
It looks at the error message from the sandbox, feeds it back to the LLM, and asks it to try and fix the code iteratively.
And what if the code runs, but the solver says, no solution found? Like the model itself is flawed?
Good question. If repairs fail, or if it gets an infeasible solution, it triggers self-verification. It goes back to square one, questioning the mathematical model itself.
So it reevaluates the initial interpretation of the problem.
Yes, and both self-repair and self-verification ultimately lead back to regenerating the code, hopefully a better version.
Okay, that sounds pretty robust. Now, to test this OR-LLM agent, the researchers didn't just use existing problems, right? They made a new benchmark.
They did. A new data set with 83 real-world OR problems. These are like textbook examples, but crucially, described in natural language, often with data tables.
Why was creating a whole new data set necessary?
Well, you need a standard way to measure progress, right? Before this, there wasn't really a good, consistent set of OR problems framed specifically for testing AI automation from natural language.
So it provides a level playing field.
Exactly. It helps compare different approaches fairly and see how well they handle realistic complexities, bridging that gap between AI theory and OR practice.
And the results. How did OR-LM-Agent stack up against other powerful LLMs?
The results were quite striking, actually. They compared it against several state-of-the-art LMs, both reasoning-focused ones and more general ones.
Yeah.
OR-LLM-Agent achieved a 100% pass rate, meaning it always generated runnable code for the benchmark problems.
Wow, perfect pass rate and accuracy.
Very high accuracy, too, around 85.5%, significantly outperforming the other LLMs used standalone.
So just throwing a powerful LLM at the problem isn't enough.
That seems to be the key takeaway. The agent framework itself, the structured approach, the COT prompting, the self-correction loops, that adds significant value beyond just the raw capability of the underlying LLM. It needs that specific guidance for this domain.
Okay, let's dig into the paper's details a bit more. The introduction really sets the stage, emphasizing that OR is powerful, but bottlenecked by the need for human experts.
Yeah, it highlights that translation step, real-world problem to mathematical model, and then the programming step as the major hurdles. Costly, slow,
And LLMs, especially these newer ones good at reasoning, seem like a potential solution.
Right. They understand language, they know math concepts, they can even generate code. It's a potent combination for this task.
The paper also mentions that earlier attempts using AI for OR code generation weren't always successful.
Correct. They often used older LLMs, less capable of complex reasoning, or involved really complicated workflows. And as we discussed, the lack of good benchmark datasets made evaluation tricky. This work tackles those issues head on.
Okay, moving to their related work section, they give a quick tour of LLM evolution transformers GPT models.
Standard background. Self-attention, NLP breakthroughs, ChatGPT, GPT-4, GPT-4o. They also responsibly mention the hallucination problem.
Which is crucial when you need mathematically correct models and working code. You can't have the AI just making things up.
Absolutely not. Precision is key here.
Then they dive deeper into chain of thought.
Yeah, explaining how just prompting the LLM to think step by step dramatically improves performance on reasoning tasks. They mention the original work by Wei et al.
And also self-consistency, where the model tries multiple reasoning paths.
Exactly, Wang et al.'s idea. Generate a few different step-by-step solutions and pick the most common or consistent outcome. Adds robustness, like getting several opinions.
It seems Cody has evolved too, from simple linear steps to more structured reasoning.
Right. And this leads into their definition of reasoning LLMs.
These aren't just standard LLMs prompted cleverly. They're specifically trained for logical inference.
That's the idea. Trained often using reinforcement learning, where getting the right answer, the accurate reasoning, is the reward signal. They're fine-tuned for tasks like math, code, science.
And they use specific prompt structures. System, user, assistant prompts, even those think tags to show internal reasoning.
Yes, that structured interaction helps guide the model's reasoning process more effectively.
Next up, code agents. What are those exactly?
Think of them as LLMs specialized for coding tasks. They don't just generate code. They can often execute it, debug it, refine it.
Like OpenAI's Codex or DeepMind's AlphaCode.
Precisely. AlphaCode, for instance, used massive sampling and filtering to find working code for competitive programming problems.
And more recent systems like AutoGen or OpenCode Interpreter involve multiple agents or more complex loops.
Yeah, AutoGen uses collaborating agents for refinement. OpenCode Interpreter integrates generation, execution, and optimization, trying to mimic how a human developer might work.
But the paper argues these existing code agents, while powerful, weren't quite right for OR.
Generally, yes. Either not focused on OR-specific modeling needs or still relying on LLMs without that strong, explicit SOTI reasoning capability that OR-LLM-Agent leverages.
Okay, and finally, they briefly touch on the OR solvers themselves.
Just a quick overview. The engines like Gurobi, CPLX, the commercial heavyweights, and important non-commercial ones like SCIP or CBC, these are the tools that actually do the optimization once the problem is formulated correctly.
Got it. So that brings us back to the OR-LLM-Agent framework itself. Can you walk us through that flow again?
Sure. It starts with the natural language problem description. That goes into the reasoning LM.
Step 1. Mathematical modeling using COT.
Right. The LLM outputs the formal mathematical model, maybe in LaTeX. Then that model is fed back into the LLM. Could be the same one, could be another instance.
Step 2. Code generation. Using the math model as input.
Yep. Generate Python code using, say, the Gurobi library. Then that code goes to the OR code agent.
Step 3. Execution and verification in the sandbox.
Exactly. The OR code agent runs it. If errors pop up, self-repair. If it runs but gives an infeasible solution or fails repair, self-verification, rechecking the math model.
And both loops lead to trying to generate better code.
Correct. The reasoning LLM is central to modeling, coding, and correcting itself based on feedback.
They specifically mention using separate prompts for the modeling and coding stages. Why not just go straight from natural language to code?
They argue the two-step process is more robust, especially for complex problems. Forcing the LLM to first explicitly define the mathematical structure helps ensure the logic is sound before trying to code it.
It prevents errors creeping in from trying to do too much at once. And maybe LLM output limits play a role.
That too. Complex models and their corresponding code can get lengthy. Breaking it down makes it more manageable for the LLM.
And the OR code agent, running in that sandbox, using self-repair based on error messages, self-verification based on feasibility, that really seems key to making it practical.
It is. It adds that crucial layer of autonomy and robustness. Without it, the first runtime error or modeling mistake would just halt the process and require human intervention.
Right. Okay, let's talk experiments. They used their new 83 problem benchmark. What were the main metrics?
Two key things. Pass rate, did the generated code actually run without crashing? And solution accuracy, did the code produce the correct optimal value or something very close to it?
They used Gurobi as the solver, and the core LLM for the agent was GPT-03 Mini, setting the temperature low for consistency.
Yes, GPT-03 Mini is noted as a reasoning LLM.
And the main comparison was OR-LLM-Agent versus other state-of-the-art LLMs trying to solve the problems directly.
Right. They tested against other reasoning LLMs like DeepSeek R1, Claude 3.7, Gemini 2.0 Flash Thinking, and non-reasoning ones like GPT-4o, DeepSeek V3, Claude 3.5.
And the results were clearly in favor of the agent.
Very clearly. OR-LLM-Agent got that 100% pass rate and around 85% accuracy, significantly better than the reasoning LLMs on their own, and vastly better than the non-reasoning LLMs.
That really underscores the value of the framework itself, not just the base LLM.
Absolutely. They even did ablation studies. They swapped GPT-03 Mini inside the agent with other models like GPT-4o or Gemini Flash.
What did that show?
It showed that while a better core reasoning LLM does improve performance within the agent framework, the agent structure itself provides a major boost compared to using those same LLMs without the agent's guidance and feedback loops.
So the agent helps even very powerful LLMs perform better on this specific task.
Exactly. It confirms the framework's contribution to both pass rate and accuracy.
Okay, let's try and boil down the key takeaways here. What are the main non-repetitive points?
All right, 1. OR-LLM-Agent automates a traditionally expert-heavy, time-consuming OR workflow. Big step.
2. Reasoning LLMs using chain of thought are critical for getting the math modeling and code generation right in this context.
3. The self-repair and self-verification in the OR code agent are vital for making the whole thing robust and reliable. It's not just a one-shot generation.
4. That new benchmark dataset they built is a really valuable contribution for future research in this area. Addresses a real gap.
And 5. The experiments strongly back up the claim that this agent-based approach outperforms just using powerful LLMs directly for OR problems.
Makes sense. So, stepping back, what are the big picture real-world implications here? This seems like it could be quite disruptive.
I think so. The biggest implication is probably the democratization of operations research.
Making it accessible to companies or groups that couldn't afford dedicated OR experts before.
Precisely. Small businesses optimizing inventory, nonprofits optimizing resource allocation, logistics companies fine-tuning routes. Things that were previously out of reach financially or technically might become feasible.
So, faster development cycles for optimization solutions.
Yes, and potentially much broader adoption of data-driven decision-making. Think about Amazon's logistics or airline scheduling. That level of optimization, while maybe not that complex initially, could become accessible much more widely.
You could see applications in supply chains, manufacturing schedules, hospital resource planning, public transport.
Anywhere complex trade-offs need to be optimized, and it reduces the cost barrier associated with hiring those very specialized personnel.
It basically lowers the barrier to entry for applying OR to a whole new class of problem.
Yeah, problems previously deemed just too complex or time-intensive to model and solve manually.
Really fascinating potential. Okay, let's shift gears slightly to our novel notions segment. Where could this research lead next? What are some, blue sky ideas?
Well, one direction I find intriguing is integrating this with real-time data streams.
So moving beyond static problem descriptions from textbooks or documents.
Exactly. The paper deals with problems described up front, but imagine connecting OR-LLM-Agent to live data feeds from IoT sensors, from business databases, from market trackers.
So like a dynamic supply chain optimization. The agent sees live traffic data, sudden demand spikes, and automatically reformulates and resolves the routing problem on the fly.
That's the kind of thing. The core capability language to model to code is there. The next leap could be building the pipelines and adaptive prompting so the agent can react dynamically to changing conditions.
Applications in smart cities. Dynamic pricing.
Huge potential for efficiency gains in really dynamic environments, reducing waste, optimizing resource use in real time.
What's a potential snag or something easily overlooked there?
Handling the noise and instability of real-time data would be critical. You'd need really robust error handling, ways to detect model drift when the world changes so much. The old model assumptions are invalid. It needs to monitor itself constantly.
Makes sense. Okay, another idea. What about explainable AI, XAI? Making the agent's reasoning understandable.
That's a really important one, I think. Right now, the OR-LLM agent gives you a solution, maybe some code, But why did it choose that specific mathematical formulation?
Yeah, the black box problem.
Exactly. Research could focus on integrating XAI techniques. Maybe the LLM could generate natural language explanations alongside the model and code, or use visualizations.
So a user could understand the trade-offs the AI considered, why certain constraints were critical, build trust in the solution.
Precisely. Trust and transparency are huge for adoption, especially in critical decisions. It could also help experts debug the AI's models or even learn new modeling tricks from the AI. It taps into that whole field of interpretable machine learning.
What's the big challenge in making complex OR models explainable?
Well, the underlying math is often very complex. Linear programming, integer programming, explaining the nuances of why a tiny change in one input leads to a big shift in the optimal solution in a way a non-expert can grasp. That's tough. It's more than just showing equations.
Yeah, translating deep mathematical relationships into intuitive explanations is hard.
Definitely.
So just our usual disclaimer, these are speculative research ideas, food for thought, not predictions.
Absolutely. But this OR-LLM-Agent paper really does open up some exciting possibilities. It's a significant step in connecting natural language to automated optimization.
If you want to dive deeper into the technicals, definitely check out the paper linked in our description.
Highly recommended.
And it leaves us with a final thought, maybe for you, the listener, to consider. As AI like this gets better at automating complex decisions, what happens to the role of the human expert? Does it shift purely to oversight, validation, asking the right questions?
That's a big question about the future of work and expertise itself. Definitely something to mull over.
Indeed. Well, thanks for joining us for this deep dive into automating operations research with AI.
Thanks for having me. Always fascinating stuff.
Until next time.